Assalamualaikum warahmatullahi wabarakatuh. In this video, we're gonna talk about vibration of couple system. So here are our group members, consists of 5 people, which is Abdul Qawiey bin Abdul Latif, Asmaa Binti Abdul Somad, Iqbal Bin Sulaiman, Muhammad Aiman Haziqh bin Amran, and me, Muhammad Hanafi bin Muhammad Sani. Before we dive deeper into our project, I would like to explain a little bit about the couple system vibration. So what is a couple system vibration or vibration of couple system? It is a branch of mechanical engineering that deals with the study of vibration and of mechanical systems that have multiple degrees of freedom. These systems are composed of two or more components that are connected to each other and their motion is not independent. The vibration of one component affects the motion of the other components, resulting in a complex pattern of vibration. This vibration can be caused by external forces or internal forces. There are several types of coupled system vibration, which are mechanical coupling. The components of the system are connected through mechanical means such as gears, belt, or shafts. Structural coupling. The components of the system are connected through a common structure such as a building or a bridge. And acoustic coupling. The components of the system are connected through sound waves. So why do we need to learn about coupled system vibration? Because it is useful and have a wide range of application, including the design of machinery, vehicles, buildings, bridges, and other structures. The understanding of coupled system vibration is that it is crucial for ensuring the safety of and reliability of this system. For our objective of the project, we will learn how the model can be built and used based on the vibration equation. And then we solve the second order differential equation of the system of vibration. And then based on the solved equation, we will do a graph that represents the equation.
In order to solve the ordinary differential equation for vibration of couple system, we use many scopes of study. We make research about vibration of couple system by searching for it in many books. We also try to find the model in articles and journals. We also try to use Newton's law and Hooke's law in this study about the mode of system vibration. Manually, we use Laplace transform to study about our model and get the general solution. To construct a graph, Maple is applied for our couple system vibration on spring graph. Maple is also useful to compare the result of general solution between manual and computer-aided solution. So this research was carried out to discover additional approaches for correctly solving differential equation problems.
Hello, I'm Asmaa Binti Abdul Somad, 018898. I will explain to you about our model. According to our readings, De Cafe and Barrett, 1977, stated that the vibration of a system of two or more coupled objects is not simple harmonic despite it is namely as undamped simple harmonic. They further stated that the vibration of the system is not considered as periodic in time, even though the object is connected by a spring force following Hooke's law. Therefore, the motion is considered as normal modes when the system themselves is moved in the simple harmony. Next, Crocker 2007 stated that undamped free vibration system is when the mass of m kilogram is placed on a spring stiffness k Newton meter. The mass is allowed to move to a distance of x to its equilibrium position depends on the weight and the acceleration of ma newtons. This is our derivation from our model. So the basic equation from the combination of the two laws, Hooke's law and the Newton's law, we know that force needed to move the mass is given by ma is equal to negative kx, where the a is the second differential of x with respect to t. So this is our model where the mass, two masses is connected with three springs. All right. To derive our equation, we have to consider the force applied to the mass with separately. So we have the two equations. First equation for m1 is equal to m1x1 double prime is equal to negative k1x1 plus k2x1 minus x2. So the first term of the equation negative k1x1 is for the forces applied to the spring 1 and the k2 x1 minus x2 is for the spring 2. We have to take into consideration of the spring 2 that connected with the two masses. Therefore, we have to consider the displacement of the mass x1 and x2. So this is our problem, normal mode of vibration in coupled system. From the figure, we know that the mass 1 and mass 2, the two masses is equal to 3 kg is interconnected with the spring, with the stiffness of the spring is K1, K2, K3 is equal to 1. Next, we have the initial condition is the position of both mass is at 0 and the initial velocity of mass 1 is 2 meter per second and the initial velocity of mass 2 is 1 meter per second. Therefore, we have the two equations. First equation is 3x1 double prime is equal to negative x1 minus x1 minus x2. And the second equation is 3x2 double prime is equal to negative x2 minus x2 minus x1.
I am Iqbal Bin Sulaiman and I will present the manual solution of the model. To make it short and clear, we will solve both equations for mass 1 and mass 2 simultaneously. The left side is for equation 1 and the right side is for the equation 2. We use Laplace transform to find x1s and x2s. Firstly, we will equate the equation equals to 0, then apply Laplace transform. Then we get for the x1s equals to x2s plus 6 over 3s squared plus 2, and for the x2s equals to x1s plus 3 divided by 3s squared plus 2. Next, for equation 1, we will insert x2s into x1s and we get the new x1s. Then from that, we will apply partial fraction and we get x1s equals to 9 over 2 3s squared plus 1 plus 1 over 2 s squared plus 1. And for the equation 2, we will insert x1s into x2s and we get the new x2s. Then we apply partial fraction and we get x2s equals to 9 over 2 3s squared plus 1 minus 1 over 2 s squared plus 1. Lastly, we apply inverse Laplace transform to get the answer for x1t and x2t. Therefore, this is the solution for ordinary differential equation for this problem.
Bismillahirrahmanirrahim. Assalamualaikum. So my name is Aiman Haziqh. I will explain about the computer aided solution. So for computer aided, we are using Maple to solve our problem. Firstly, we declare the equations of the problem. These general equations have been explained previously by Asmaa. Then we substitute the value of M1, M2, and K1, K2, and K3 based on the problem and solve it. As you can see here, there's an expand function to make the equation more neat and simple. After that, here we declare again the equations of the problem with initial conditions and the derivative of initial conditions for each equation. In method, we can just directly solve the general equations, so there's no need to do the Laplace and other calculations like in manual calculation. Moving on, to find the general solutions of the problem, we can just simply type this solve function and call the equation that we want to solve. So that's the this is our general solution. Here's to evaluate this solution. So for each equation 1 and equation 2, and lastly, plot the vibration of couple system on string graph.
As a conclusion, the vibration of coupled system has two second-order ordinary differential equations, and we can solve the equation using the Laplace transform of the initial value problem, or IVP. We use Maple as a computer-aided approach and compare its general solutions result to those of a manual solution. Then we also provided the graph. Of vibration of a coupled system on the spring. As a recommendation, we can improve our current model, which is the motion of a two-mass system with 2 degrees of freedom to become a more complex system. For example, we can improve our model by using 3 masses connected by 4 springs. For more than 2 masses, it is easier if we use matrix form to solve the differential equation. Besides that, we also can use either different masses of the block or different stiffness of the spring. Furthermore, we can improve our model by accounting for the external forces like friction involved in it. That's all for our presentation. Thank you.